This time I'm going to talk about monitoring weeds so that we can predict crop yield losses. I will focus on the various methods of assessing the weeds. So let me start presenting. So weeds monitoring for control measures and predicting crop yield losses. So here we've got a field of maize with weeds. How can we estimate the impact of these weeds in the crop? How much of the crop yield loss is due to these weeds? Now, if we look at weed seedling emergence, weeds will be sampled in the cropping fields using a 45 times 45 quadrat. Individual weed species would be counted and recorded. We can also calculate the following parameters: weed density. There's something called weed species richness, weed diversity, Shannon-Wiener diversity index H, and the weed evenness. Even with the insect pests, we can also calculate similar indices. Insect density, insect species richness, insect pest diversity, insect pest evenness, something like that. So here is a quadrat where we can count our weeds. We can also, instead of counting, we can use the leaf area and the relative cover. We can determine leaf area of crops and weeds. We can also visually determine percentage cover of crops and weeds. We can use the GIS application techniques. We can also sample for weed seeds in the soil to assess the weed seed banks. So we can take soils from depth of 0 to 10, 20 to 30, and 10 to 20 and 20 to 30. The soils will be put in shallow trays to encourage germination and weed seedling emergence. Weed seedling emergence are recorded every 2 weeks in August, September, and October. We can estimate the weed seed bank sizes through weed forecasting. Or we can do weed forecasting. Here's the field where we can use quadrat, which is 45 times 45, to sample for weeds. We can use what are known as additive experiments to assess crop yield losses. So some of the research questions which we may want to ask may be: first, what is the minimum weed density which justifies weed control. This is like a weed control threshold. What is the most competitive weed? We can also assess this. And of course, we are interested in crop yield loss. Now, we can use pot experiments where we can vary weed density in pots whilst we maintain the crop density constant. Like in this case, we maintain one crop plant per pot against various weed densities. So weed density can be varied, for example, 0, 2, 4, 6, 8, 10, and 12 plants per pot, while crop density is held constant. And we can use one plant per pot. The treatments are replicated in RCBD or CRD, but mostly CRBD. The data collected is crop height, crop biomass, leaf area, and weed biomass, but mostly crop biomass is important. Normally, we use regression analysis in these studies. For example, we can use linear quadratic response, exponential curve, hyperbolic curve, or sigmoidal curve. What is the effect of weed density on crop yield? What is the weed density which justifies control of weeds in order to avoid economic yield loss? This is our weed control threshold. Should we monitor weed populations in cropping fields in order to plan weed control programs? Is weed density the best tool for predicting crop yield loss? Is data collected from one weed species applicable to fields with mixed weeds? These are some of the issues which affect these studies. We are going to focus on the Zimdar and the Cousins proposed models. Here we are looking at effect of weed density on crop yield. This is according to Zimdar. The loss looks like a sigmoid curve, where initially it's stable, then it starts decreasing very fast. That is the crop yield. Then it stabilizes towards the end. If you look at the crop yield loss, it starts as stable at the beginning, then we have a steep loss, then again it stabilizes. This is a sigmoidal curve, which was proposed by Zimdar. However, Cousins proposed that as long as there are weeds, we should get a loss. So he proposed a rectangular hyperbola, which is this curve. So as we increase weed density, we get a hyperbolic curve. Again, when you look at the crop yield loss, it's also in the form of rectangular hyperbola. At first, you have a steep increase, then it stabilizes at what is known as the maximum yield loss, represented by A. Here on the slope, we have got I, which is representing the slope. So we've got two ways of showing yield loss, either the Zimdar approach or the cousins approach. According to cousins, we can have an equation to predict yield loss represented by YL, which is equal to slope, which is I, multiplied by width density, now divided by 1 plus, or in brackets, slope width density divided by A, which is the maximum yield loss. Now, Croft and Spitters in 1991 proposed that relative leaf area was more appropriate rather than with counts. Now, relative leaf area is the leaf area of the width divided by, it's the leaf area index of the width divided by the sum of the leaf area index of the crop and the leaf area index of the width. Again, you also get a rectangular hyperbola, but here we now have a relative leaf area of width instead of width numbers. Now this is represented by LW, and we have this crop yield loss. Now the equation for crop yield loss becomes Q multiplied by relative leaf area, all divided by 1 plus, or in brackets, Q, which is the slope, divided by the maximum yield loss, which is A, minus 1, or in brackets, multiplied by leaf area of the width. So again, it's the same equation for yield loss, which I was trying to explain, where you have Q, which is the slope, multiplied by the leaf area of the width, relative leaf area, divided by 1 plus, or in brackets, Q, divided by A, which is maximum maximum yield loss, minus 1, or in brackets, multiplied by relative leaf area. Or alternatively, we can use an easier estimate. This one is easier to measure rather than leaf area. This is relative cover, RC, where we have the area covered by the width divided by the area covered by the width plus area covered by the crop. Again, you get this relationship, which is a rectangular hyperbola, where you have relative cover of the width, RC, plotted against the crop yield loss. You get this curve, which is a maximum yield loss represented by A, and the slope represented by Q. Again, yield loss is equal to Q, which is slope, multiplied by relative cover, all divided by 1 plus everything in brackets, Q over A minus 1, multiplied by RC. Okay, this is what I was trying to explain, where you can estimate yield loss using this equation. Now I want to talk about something which is a bit different from weed density. Time when weeds are removed from the crop is very important. Although weed density is important, but the time when those weeds are removed is even more important. So the question is, how long should hoe weeding be delayed before there is crop yield loss? Is it 1 week, 2 weeks, up to probably 6 weeks? Or how long must be a crop be free of weeds to prevent crop yield loss? Is it 1 week, 2 weeks, or up to 8 weeks? So if we look at the life cycle of a crop, number one, there's period when weeds do not compete with the crop. This is the first few days after crop emergence and the days before crop reaches maturity. Number two, there's a period when weeds compete with the crop from 2 weeks to 6 weeks after crop emergence. Now, there's what we call the critical period for weed control, which starts from the time when a delay in weed control results in significant crop yield losses and extends to the time when weed control does not result in significant effects in increasing crop yields. So during the crop life cycle, there's a period when the crop is sensitive to weeds, and another period when the crop is insensitive to weeds. So the time when the crop is sensitive to weeds, that is the critical period for weed control. Now, sometime in 1968, a scientist known as Nieto in Mexico proposed some interesting treatments to assess the critical period for weed control. We have got two groups of treatments: the weed period, where you have zero, no weeds. Then you can vary the weed period from 2, 4, 6, and 8 weeks. Then we have what we call the weed-free period in weeks, where you can vary this period from 0, where you have weeds. Then we have 2, 4, 6, and 8 weeks, in which case where you don't have weeds. Now, the data which we obtain from such an experiment can be used to plot two graphs which are superimposed, which can illustrate the presence of the critical period for weed control. Now, on the x-axis, we have got time in weeks. Now, let us look at treatments when we are delaying weeding. This is represented by this black curve. As we increase the delay period from 2, 0, 2, 4, 6, 8, and so on, at first we yield is stabilized, then it started decreasing. Now, if we were supplying the crop with a weed-free period, making sure there are no weeds for different times, we could increase crop yield versus weed-free periods up to this point, represented by this red line. So if we draw these two graphs together, they can enable us to identify this part here. How we get to this part is that if we allow probably 10% yield loss as not being important, or even 5%, or even zero, depending what you want, we can draw now this is straight line. Where it cuts off this point, we mark it, and where it cuts off this point, we mark it. So from this point to that point is what is defined as the critical period for weed control. This is the time when the crop is very sensitive to weeding. So as far as the weeds are concerned, weed density, the leaf area, or relative cover is very important to assess crop yields. But also the time when these weeds are being removed during the life cycle of the crop is equally important. So this is it. So this is the end of this lecture. I will have to stop sharing. So we've just talked about the effects of weeds on crop yields. Just like we were talking about the effects of plant diseases on crop yields. So I will have to stop here.